Hey, 13s, I'm back! That was fast, wasn't it? It's like a double chem lesson. And yes, I'm drinking green tea and ginger out of a out of a beaker with a handle on the end of it. It's amazing, let's say. Kane's asked a really nice question. Before I do that, I'm just gonna whoa, a beaker with a handle on the end of it. It's amazing. Let me turn that off. Pop the chat out. Kane, you've asked a lovely question. So, yeah, molecules are that flexible. When they're short, of course, they're less flexible. Once you get like beyond 5 and 6, they're like bend. They're like, especially depending on the temperature. You realize that the longer the chain is, the lower the temperature needed for that cyclopolymerization to occur. And yeah, they are that bendy. The higher the temperature you get, the more bendy they get, the more wobbly they get. Winket's absolutely right. There's, you've got polar ends of these molecules, and so they're going to be doing all kinds of funky things while they're flexible. There'll be attractions all over the place. But in reality, I think it's more about the flexibility in molecule and the temperature and the collision between the acid and base group for them to link. So, but yeah, really interesting. So I'm just plowing on, guys. I could do this lesson tomorrow on azo dyes, but I figured I may as well just get it done. Let's just get it done. And then maybe tomorrow I can do some exam question review, because, oh my God, are the organic questions tough. Like, we need to seriously spend some time looking at these questions. They're really hard. I will do as many exam review papers as I can as we move towards your final exams at the end of the year, even though they're mocks, they're not real exams, but I will do as many as I can. Okay, so azo dyes, lesson 3, nitrogen chemistry. Let's get it boxed off. So I will first of all shift my cam over to my clip cam. Oh, there's my other half being so lovely. Just gives you a wave. Let's then share my screen. There we go. Let's just crack on with azo dyes. Now, edXL do want you to know one. Can we postpone the marks? Yeah, I'm gonna say no. No. So I think that's all up and running now. So I put the link onto the chat. Yeah, we're all there. So this is nitrogen chemistry lesson 3, azo dyes, and this pretty much brings nitrogen chemistry to an end, apart from polyamides. But of course, in reality, I'm going to do that as part of the polymers topic. So, and that, of course, we'll just link in. So, azo dye lesson 3. This is actually going to be a short one, which is good, because we are now specifically focusing on a really, really small section. But they do ask these questions on a regular basis. You need structures, and so it's worthwhile doing this. So, azo dyes, learning objectives. Understand the formation of the diazonium ion. Next, number 2, and be able to draw those, by the way. Next, know the conditions and why. Yeah, so recognizing why we're doing, not just are they going to ask you to spit out a condition, but they're also going to say, why does it need to be like this? And then the last one is be able to draw simple azo dyes. edXL focused on a very particular azo dye, which is a rather odd structure because basically all the others kind of go a slightly different way. But it doesn't matter. We can just focus on that one. I will mention the others as well. Okay, let's flip over to tablet mode. Okay. So we now drop back once again to an amine, good old phenol amine. So azo dyes. So azo dyes, number 1, organic molecules that have colors. Now, the reason why I mention this is because, of course, you've been studying colors in transition metals. If you haven't seen my transition metals series, please go away and watch my transition metals series. Transition metals were one of the original synthetic colors that we used to use in paints and all kinds of stuff. But the problem with transition metals is they're massively toxic. So we needed to find a replacement for transition metal complexes for colors that was way less toxic, and really that would just flat out better. And these are then, of course, used, so azo dyes, next, used to color fabrics. Yeah, color fabrics. They're also used to color fabrics, used as indicators. Indicators. The main one is methyl orange. Methyl orange is an azo dye. Isn't that amazing? Are they used as food colorings? I wish people want to go back to. Will people want to go back to school? Winky, I don't know. You should want to go back to school. It'd be nice to actually make some azo dyes and all that. That'd be fun. Used as indicators. Do they have azo dyes as food colorings? Possibly. They're very stable molecules. Once they've been formed, they're relatively non-toxic. Assume they do. But anyway, those are the only two that you need. They're used as to color fabrics, and some are used as indicators. Okay. So the next thing is, how do we make them? So, oh no, we need to talk about the azo linkage is what we need to talk about. Okay, so making. So the making process essentially is a two-step process. Making azo dyes. So the first step, making azo dyes. So two-step process. Two-step process. There we go. Two-step process. The first one, hi Sophia. Sophia, this is an A2 chemistry lesson, and it is a bit mental. Sounds like you're talking about Voldemort. Okay. The instant that may not be named. So two-step process. Step one, I'm going to change my color. Whoa. Okay, a bit thick. Step one is the formation. Step one, formation of the diazonium ion. Let me show you what that looks like. So hang on, step number 2, followed by step 2, which is called, my laptop had a brief heart attack there. Step 2 is called a coupling reaction. Okay, so we need to look at each of these in turn. So we now drop back. We're going to do the most basic azo, the simplest azo dye. Yeah, what we're going to do is we're going to focus on phenylamine. Now you're going to notice that I draw it in a very particular way. Yeah, I'm trying to draw this so that the benzene is on its side and the amine group is sticking out here. So we start off with phenylamine. Phenylamine. Now what we need to do is we need to form the diazonium ion. Now in order to do this, now this is where Edexcel are a bit odd. They require one reagent and one temperature, and it's not entirely correct, which is a bit irritating. What we need to know is that we are going to add nitrous. Sodium nitrite. Sodium nitrite. Oh, but then it should be HCl. Sodium nitrite and HCl at 5 degrees Celsius. I need to check that. And it's not on the specification either. But that's what I've seen on exam papers. Oh, blimey, it's going to be impossible for me to find this now, isn't it? There's no, like, these papers are so hard. You need to realize how hard. Paper 5 is the hardest chemistry paper that you'll ever sit. It's a bit crazy. Oh, I'm never going to be able to find this. But I'm pretty sure that's what they want. Sodium nitrite and HCl. The reason being is you can't just use nitrous acid. Oh, this is going to be a nightmare. June 2016. I want to find the question. This is being a right pain. Oh, no. Uh-oh. Oh, is this it? That's just no. Nope. Oh, man. I'm not going to be able to find this now. Sodium nitrite and HCl. There's an azo dye. Right. Explain the content. Really? Really? Prussian blue is there. Discovered was one of the first dipping paints. Methyl red is an azo dye. Carbon. What? I don't want any of that. Oh, there it is. Give the reagents conditions for step number 1. Yes, that's what I want. Right, what question number is this? This is question number 23, June 16. June 16, 23D.1. June 2016. June 2016, mark scheme. I found it. So they're gonna say this is question 23D, part 1. Sodium nitrite and HCl. Allow nitrous acid. And HCl. How bizarre. Okay. Fine. Let's. Okay, I'm happy with this now. Fine. And look, there's the 5 degrees. Yeah. So now you don't need to know a mechanism for this, guys. You really, really don't. I can do it. Oh man, would I really want to try and do that? It can be done. I can do it. I don't want to. I'm going to get myself lost in something I don't need you guys to know. Now, what happens here is you now form this scenario. You now form that scenario. Like that. So, I know it looks really, really weird. Yeah, I wonder if I go back to the 2060, it's quite nice to look at this from a question perspective, because it gives us a little bit of context. Like I was saying, that the questions are really hard, and there you go, there it is. Yeah, and then you can see that there's a Cl attached onto this at the side. But in reality, this section here is called the diazonium ion. Now, I said to you that you need to know the reactants and the conditions. Well, here are the reactants, yeah, and here is the condition. And I said to you, you need to know Y for the condition. Yeah, now the Y, which is here, yeah, Y 5 degrees Celsius. So you can add this on. So exam question, Y 5 degrees Celsius. They will just say, explain the condition. That's actually what they'll say. Explain the condition. Explain condition. The reason for this is the diazonium ion is not stable. And if this warms up, it'll reversible forward as exo. No. Good idea, Winkit. Good idea. It's more than that. It will go through thermal decomposition. And since the HCl is not conc, it's dilute, there's water around, it'll then react with water and turn into phenol and nitrogen gas. So the explanation for the condition, explain conditions, the answer is above 5 degrees Celsius, the diazonium ion will decompose, will break down. decompose. And as I said, it's actually more than that. It'll just turn into phenol. It'll react with water at that point. But they just want you to say it decomposes. It breaks down, falls apart. So we've got to keep this below 10 degrees. It actually says between 0 and 10, just learn 5. Yeah, that's the temperature you keep it at. It's actually really difficult because you have to essentially use like an ice bath to do this. But then, oh, this is driving me nuts. I'm going to get rid of my laptop is having a major problem with its bloody detachable keyboard. And I'm just going to, no, it's all right. I don't need it. It's just causing my laptop to flip in and out of tablet mode. I forgot what I was saying there. Decompose. No, lost it. Lost it entirely. Damn it. Anyone want to fill me in on what I was saying? Yeah. Anyway. I was saying that you had to keep, you had to use a water bath. But it's a nightmare because the water bath is got to be kept below room temperature. So you need to chill it. And if you use the ice, well, then the ice is going to melt. You're going to get fluctuations. It's an exothermic reaction to forward, so it heats up. Yeah, so you've got to keep adding. It's a nightmare. Real nightmare. If they do that, though, just if they asked how you would do this, you would just say in an ice bath. Yeah, you can't say in a cooling bath. It's not okay. Isn't that weird? You have to say in an ice bath. So it's just a bit of an odd thing, really. It's actually really tricky to do. There are other reactions you have to keep cold, otherwise you get multiple substitutions. But in this case, it's because the diazonium will break down. Right. Now that we've formed the diazonium ion, what we now need, that is step number 1. Yeah, step number 2 is coupling. So what we now want to do is we want to take the diazonium ion. This is step number 2. Yeah, S2, coupling. So you take the diazonium ion, which is rather odd because the nitrogen, the second nitrogen is, and will it explode? Well, when you're doing, no, it'll just produce nitrogen gas and decompose and bubble away, and it'll just go, it won't explode, no. Once you've got this, what we now need to do is we need to couple it, and Edexcel, very clear on this, say, you need to learn how to couple to phenol. I want to see that. Watch some YouTube videos. We can actually make these in school. I bought last year, at the end of last year, I ordered everything to make azo dyes. We can make some in school. When you get into school, we will do it. Yeah, we'll just make a couple of azo dyes of different colors. So this reaction, what we now need to do is we need to couple. We need to link these two molecules together. And they do this very specifically with phenol. It's actually on your, by the way, but then it's interesting to look at the question. Check that out. Yeah, they're not coupling this to phenol this time. They're coupling it with this monster over here. I don't know if you can see my pen or not. It's really weird though. But yeah, so they're coupling, it's nice to say this, they're coupling with this guy, whereas you guys learn the coupling to phenol. And there is relationships here. Can you do it with the big class 2? Oh, darn it. Yes, I can. We can do it, we'll do it after school one day. So there's no rush to leave the class. Yeah, that's what we'll do. We'll do it as an after school project, and you guys can all take home your azo dyes and have a go at doing some tie-dye t-shirts at home. Can do it. We can even do the tie-dye t-shirts at school. Oh, funny. Anyway, so what we need to do is we now need to link, the word coupling means to link. So what we need to do is these are going to join. Now, this is why Edexcel focus on this one, and it is a bit odd. Yeah, the coupling becomes this. This is what the coupling looks like. Yeah, like that. So there is the azo dye. So the thing to just pick up on is that with phenol, the phenol group is attached to this carbon here, and the coupling will go on the opposite side. Accidentally spills azo dyes on shirt, cries. Wink it, yeah, been there, done that. Yeah, I've ruined loads of shirts with azo dyes. Yeah, I usually end up then giving them to students and I do a stupid pattern. I paint them with azo dyes and just give them away. But the thing is, all you need to know actually for this process is that it is coupled using sodium hydroxide. That is all you need to know. Once you've got the diazonium at 5 degrees Celsius, I'll show you the YouTube video of people doing this. You add the phenol, you add sodium hydroxide, and they will couple together. So just to explain what is, now you don't need any more information, as you can see from this diagram. So it says, so it's given us a perfect azo-dye synthesis. This is called anthranilic acid, and we're going to make methyl red, which is an indicator. So what we've done is step number 1 in this one is to use sodium nitrite, NaNO2, not NO3, yeah, and HCl, 5 degrees, and I'm going to end up with my diazonium ion up here in the top corner. I think I've already snipped this. Yeah, so we know that this is NaNO2, HCl, 5 degrees Celsius. We form our diazonium ion, and then we need to add this disgusting monster with sodium hydroxide. Yeah, and they will link together. Let's look at where the question then progresses. So it says step 2 involves the reaction, which a similar reaction to the diazonium ion and phenol suggests the structure of the organic compound which reacts with the diazonium ion to form methyl red. So all you need is to draw that stupid thing. That's it. That's the structure. And it's very interesting, isn't it? It's a tertiary amine. So that is NN dimethyl phenyl amine. They're going to ask you to name it, aren't they? They're going to do it. They're going to say name it. Use information on page to suggest the acid alkali types from methyl reds most. Oh, that's stupid. At that point, they've left the whole process, but relatively straightforward. So it is worthwhile at this point. We're kind of done. I do want to mention some other questions, though. I think it's worthwhile me just scrolling through a couple of papers to show you some more of these azotes. So that was the June 2016 IAL. Let's go for the June 2015 and find the azo-dye question. They're usually in the long answer. Oh, phenol reactions did this earlier. When phenol reacts with excess bromine water, B, did that with you last lesson on YouTube. Yeah. Oh, look, there's the amine question of increasing pH. That's interesting. Increasing pH. So hang on a minute, that's not correct. So we know that ammonia that's a great question right there. This, you now understand why I'm teaching you. Oh, that is definitely not what I wanted. I just screenshotted my screenshot. Lol. So this one, really lovely question. This is why I'm teaching you nitrogen chemistry. We know that ammonia is 11. Butylamine is a primary amine. That's 12. And phenylamine is 9. So increasing pH, the butyl will need to go last. In order of increasing pH, that makes sense. 9, 11, 12, I'm done. Thank you very much. Isn't that lovely? Ah, the diazonium ion, there we go. So it says the aromatic amine is converted into what is the most suitable reagents and conditions for this particular one. So it is C. Yeah, the sodium nitrate, hydrochloric acid, and 5 degrees Celsius. There's a polymer question, and polyphenol, doing that in the next one. Yeah, oh. This compound gives a precipitate, that's carbonyl chemistry, so I'm going to skip that one. I'm going to go down and see if I can track down the picture. I want to find another azo-dye, the organic questions, because they're incredibly difficult. Crystalline sulfate, no, that's recrystallization. NMR, right. Organic compound structures 1, so it's a continuation of the NMR. Go on. Right. What's this about? Yeah, use your knowledge of electrophilic substitution reactions to suggest the structure of the electrophile that might be used in this reaction. A student suggested that eugenol could be prepared by electrophilic substitution of 2-methoxyphenol, which is produced in the guts of desert locusts. This compound is one of the main components in pheromones, which can cause locusts to swarm. The structure is shown here. So we want to make eugenol from that. Right, so suggest the structure of the electrophile. So you can see what we're trying to add. I'll just take a screenshot of that. I'm doing benzene electro sub here now, guys. I'm not in azo dyes. There's the attachment I've put on. So what I'm going to do is I'm going to draw that out, the structure, yeah, and then I'm going to add a chlorine onto it. That's the electrophile. Oh, no, it's not. The electrophile is now to get rid of the Cl. They want the electrophile. That's the electrophile. Yeah, because we've removed the chlorine with AlCl3. Clever question or what? Yeah. Next, suggest the mechanism. All good. Oh, is this an azo dye? It's not an azo dye. Give me an azo dye. That didn't have one. It was in multiple choice. That was 2015's paper. Let's go for, I don't know, June 2017. I don't know. Just looking for the azo dye stuff. Oh, God, did I see white precipitates? Oh, did I see diazonium chloride? Way, we're there. Yes. Okay, so we've got benzene. Then we've got nitrobenzene. Oh, check that out. I like it. Identify the substance used to convert benzene in step number 1. The substance is. So that one there for step number 1 is conc nitric and conc sulfuric. Yeah. Give the mechanism for reaction that takes place. That's just, and then include the arrows. So that's just going to be electrophilic substitution with the mechanism of curly arrows. Nice and easy. Identify compound X and state the reagents needed to prepare it. Right, so we've gone from nitrobenzene, then in order we need to get to phenylamine. So that's going to be tin and HCl. Yes, tin and HCl is going to make it turn into phenylamine. Then they're dropping us into step number 3 to make the diazonium ion. So the compound X is phenylamine. The reagents are tin and HCl. State the reagents and conditions needed to turn X into the diazonium chloride. Reagents, sodium nitrite and HCl, conditions 5 degrees Celsius. The diazonium ion is used to prepare dyes. Write an equation for the benzene of your choice in which the production is dyes. Show the structure of the dye in your equation. Right, we're just going to do this with phenol. That's all you're going to do. Phenol, phenol, phenol. So we're taking the diazonium ion, a balanced equation. Yeah, N1, 2, 3, and then the plus there. We're going to then draw, and they want, does it say write an equation? Plus phenol. Yeah, you're just going to write, whoa, that was a terrible benzene ring. That was impressive. I'm usually better than that. There you go, plus phenol. And then you're going to form, the question is there a byproduct? Let's have a look. So we form this, the azide, azo linkage, azo dye. And you now get the OH at the other end of it. There we go. The question is now, there's an issue here. Conservation of charge. Oh, yeah. Whoa. Because that was technically a chloride, and we had an invisible H here. There was an invisible H on the benzene, which is now gone. So the byproduct is HCl. That I want to see the answer to. The benzene duct can be converted into benzoic acid in 2 steps. The first step is a substitution to produce the nitrile. State the reagent needed for the second step. Conc sulfuric acid, turn it into an acid. Hydrolysis. Conc HCl. Interesting. All these questions are all really tough, folks. So got to check the mark scheme for that one to see the balanced equation, structure of the dye. Can be converted. Yeah. By the way, just to tell you how you do that, you actually just make the benzene diazonium chloride ion, but then you warm it up. It decomposes into phenol, reacts with water to form phenol and nitrogen. Then you take phenol and you oxidize it with potassium dichromate to end up with benzene carboxylic acid. Oh, no, you wouldn't. You wouldn't. I tell a lie. Oh, I don't know what you're going to do. That's weird. Oh, how would I do that? You don't want to take the benzoate and then you're going to, because I can just have it turn into phenol. Then I can swap the OH on the phenol group for a Cl. Can I do that? I don't know. Don't know my phenol reactions well enough. Decomposes when it is warmed. The products are a colorless unreactive gas, hydrochloric acid, and an aryl aromatic compound. A white precipitate forms with bromine water, which is phenol. Write a balanced equation for the decomposition and give the formula of the white precipitate. Holy moly, guys, this had everything on it. That's so cool. They're even making you do the decomposition. So I'm going to add the decomposition to my notes. So decomposition of diazonium ion. It's nice to now add it, diazonium ion. So let's keep it simple. Yeah, let's keep it as simple as possible. Yeah, so 1, 2, 3, positive. Right. It's not really so much decomposing, so much as reacting with water. Yeah, you do need the water to be there. Yeah, so it's not really a decomposition. It's a hydrolysis, really. You form phenol. So the OH goes onto there. You also form nitrogen gas. But remember that this is the diazonium chloride has the chloride. You just don't tend to include it in the diagrams of the mechanism because it's a spectator. But what you realize is you've got a balance for the H's. So you do get HCl. So I would actually do the equation. I would actually do it as this plus water. That's going to be really fascinating to see that and see what they wanted in the pictures. Because now it adds up, you see. Everything adds up. Really, really interesting. So they're giving it so, and there's the, my laptop's doing something really annoying. It's not even the keyboard that's causing the problem. There is the colorless unreactive gas. Colorless unreactive gas of nitrogen. God, if you hadn't actually done any of these things, unreactive gas. You've also got, of course, a corrosive gas and like the phenol. So now they then did a separate reaction with bromine water, Br2 aqueous. We know from the start of the previous lesson, that phenol does this really funky reaction with bromine water, yeah, where it gets a tri-substitution, yeah, to form this guy, which is a white precipitate, white PPT, yeah, 2,4,6-tribromophenol. Look them up. Definitely want to see mark schemes for this. Yeah, state symbols not required. Balanced equation. So that was June 17. June 17, let's have a look at the mark scheme. 2,4,6-tribromophenol. Yes, Winkit, spot on. Do you need sulfuric acid as well? Where's the sulfuric acid? What do you want the sulfuric acid for? Oops, I hit the picture. Oh, that wasn't the paper. Oh no. Oh no. I thought that was June 17. Have I just lost the question I've just done? Oh, nuts. I've just lost the question I was doing. I'm sure it said June 17. Was it June 17 IAL? Make more sense, I guess. No, I've lost it. What question was I doing, folks? Oh, no. What question was I doing? Somebody help me. Oh, no. June 16, what have I done? Oh, there's another azo digress. Is this the one? No, it wasn't that one. Oh, no. I'm sure it was 17. Do not check. Oh, man, I've got royally gone and royally stuffed this up, haven't I? There's another azo die. Oh, man. What was it, guys? Someone help me. History. All right. It's not going to show me the papers I was looking at. Oh, no. There aren't even that many papers. Was it 2015? I've royally gone and stuffed this up. Oh, I think it might have been this one. Eugenol. I remember looking at the Eugenol and thinking he wasn't there. Wow, nuts. Somebody help me! Go and stuff this up, guys. Somebody please help me. Oh my God, look at all that horrible organic stuff there. I've gone and royally stuffed this up. Someone find it for me! Everyone's just gone quiet and has abandoned me. You've all abandoned me. That's what you've done. Orleban. Oh, was this it? Is it here straight off? Was it there? Yes, I found it. So why does this say June 17 on it? Oh, that wasn't my fault. Look, June 17. GCE June. This is June 17 GCE. June 17 GCE mark scheme. That's what I clicked on. Oh, but it was just high. I actually clicked on the first one. I'm so sorry. It was the right one. I didn't realize. I thought the question was more at the end. Oops. Okay. So usual things. There's the tin and HCl. Yeah, and then it says sodium nitrite and hydrochloric acid, 5 degrees Celsius. Equation, there you go. Yeah, structure's allowed, but the Cl's there. Like it. Yeah. And then hydrochloric acid, any strong acid. Also followed by 20C. What was the 20C bit? Was that the conversion? Assume it was. It's the conversion of the cyanide group to the carbon. It looks like the one you're on now. Yeah. There's the equation. There's the decomposition with the water. There you go. And there's the reject monobromophenols. Allow Kekulé structure. How fascinating. Anyway. That actually brings me to the end of my lesson today, guys. I don't need to waste your time any longer on this. I'm happy to do some exams. There were so many of these and you need to be practicing them. They are hard, man. Like this organics is now tough. And the more papers you practice, the better you get at it. So I will leave you guys be. We're done. Nitrogen chemistry is boxed off. Next one is polymers. So I will leave you guys be. Have a nice rest of your day. See you soon.